All right, so we have seen the color reproduction scheme, which is a 3 by 3 set of equations solving issue. And when we normalize everything with respect to the white color reproduction, that would make the 3 stimulus value. Proceeding from 3 stimulus, I will indicate a few more terminology, but before that, it may be okay to talk about the luminance and so-called luminosity. Luminance means in brightness or intensity in some sense, and it is like the combination all the color, of all the color coefficients to form an overall brightness for a point. So it's like we have the reproduction. So it's a new item that I'm talking about. Y, which is the luminance I'm talking about. So this is luminance. Luminance is the integral of actually the color, or by color I mean the whole spectrum, times the sensor, which is the combination of all the sensors, integrated. So maybe before this, I have to put something here. I will be talking about V of lambda, which is like S1 of lambda plus S2 of lambda plus S3 of lambda. If you look at the notes at the very beginning, or maybe I should scroll all the way up. Sorry for the fast change, but I will do that. Yeah, it's here. The red curve that I have drawn here is actually the curve of V of lambda that I'm talking about. V of lambda that I'm talking about. Okay, and that is the V of lambda that I'm talking about here. So it's a combination of all these 3 separate light gathering or sensor responses of blue, green, and red. It's a combination, it's summation of that, which is again some blob shape like that. So that is V of lambda. Now with that V of lambda, let's come back here. With that V of lambda, I will be first generating a color, K, for all K, from 1 to 3, of course, Bk times Pk of lambda, which are the light sources, times V of lambda, d lambda. This is the overall brightness of that point. Again, by interchanging some of the terms here. By the way, this beta k can also be replaced by the white k times the 3 stimulus tk, or tk of lambda if you wish to say. So I will rewrite this by changing the places, the orders of summation. This is k from 1 to 3, of course. Let's not forget this. Times tk times white of k times the ones that are related with wavelength lambda, which is pk of lambda times v of lambda d lambda. And over here, this much of it has been given a name of L sub k, which is the luminosity coefficient of source pk of lambda. So how bright is this light source or color source? It is this much. If you have that luminosity just notated as L of k, then this summation of luminance that we have is automatically becoming k from 1 to 3 tk times lk. This is the luminosity. All right. So if luminosity or luminance is of concern, I mean, in terms of terminology, these are the things that you're supposed to know and remember. Now, a few more historic terminology. We have seen previously Tk to be equal to beta k divided by Wk, which are the beta k's for reproducing white. Now, furthermore, I will define a lowercase tk, it's a definition, as tk divided by T1 plus T2 plus T3. So I am further normalizing the three stimulus values, which are normalized between 0 and 1. And this new thing will have now a different name. It's not going to be the three stimulus, but it will be notated as chromaticity. Chromaticity. And it has a nice property of T1 plus T2 plus T3 to be equal to 1. They all sum up to 1. Since they sum up to 1, it gives us a freedom of representation over only, let's say, T1 and T2 axis. The chromaticity diagram is like this. And T1 plus T2 plus T3 is equal to 1. So we can just draw it along T1 and T2. T3 is whatever is left or remaining. So our chromaticity diagram really appears in a two-dimensional space like this. And people just tend to describe their or present their chromaticity diagrams for their television screens, TV screens. For example, Apple has been using this thing, or Samsung is just presenting their chromaticity diagram to illustrate how well or how accurately their screens are reproducing the human visual system. We don't have T3 because T3 is 1 minus T1 minus T2, okay? This is the place that can be reproduced, and in general, biological, the human visual system chromaticity diagram is something like this. Like this. So it means that if it fits into the chromaticity diagram of your screen, color reproduction system, then it means that the places where they're not shaded, but inside this red D shape, are the ones that you are unable to reproduce. So your TV is incapable of reproducing, for example, this color here, which can be seen. Why can it why is it not reproducible? Why is that point not reproducible? Because of the voltage limits, most probably. We cannot apply that kind of a voltage. And furthermore, T3 must be something negative. Or similarly here, this one says T1 is negative, so it can't be reproduced. However, there are a few interesting places like this sort of triangular shaded area. That area is a place where the TV screen is capable of reproducing some colors which the human eye cannot perceive. That's also a possibility. We want to fit that D shape or tongue-shaped thing as much as possible to fit inside this triangle. Or we want to enlarge our triangle in such a way that it includes most of this red shape, okay, for a good television. And the ones that are reproducible and visible altogether are called, it's also given a name. Let me shade them in blue here. This blue part is notated as the color gamut. I don't really know how to spell it, how to pronounce this one. It may not be English, I don't know. So this is the color gamut, which means your TV is reproducing these colors. If you can quantize this to some levels, you can say or give a number of totally reproducible, distinguishable colors, and usually they are notated in terms of millions. So that this is what a color gamut is. Okay, these are some historical purposes, and they don't serve for solving questions in a final examination, in a final take-home examination. So the question that may be of interest at this point may be, what kind of a question can be asked from here? And the question that can be asked will be mostly related to the system of equations, to the formation of system of equations that I have given at the very top. So the example where I will probably ask a question similar to this one would be like this. I can give you 3 light sources for blue, green, and red. And they may be this. Of course, the starting and ending points must be given to you. Then this. And red. For instance, this. So we have these 3 shapes. These are the color sources or light sources. Okay. These color sources are like your lamps. Okay, you have these 3 lamps. These points are given to you as A, B, C, D, E, and F. Okay, over the wavelength. And this intensity is x1. This is x2. I will give you some numerical values for this. And then these are the color sources. And then I have the human visual system. The human visual system is, it can be a half circle for the blue and a triangle for the green and this rectangle for the red. And these are the eye sensors. Okay, so these are the color sources pk of lambda. We have p1 of lambda, p2 of lambda, and p3 of lambda. And these eye sensors are s1 of lambda, s2 of lambda, and s3 of lambda, which may be notated as si of lambda. These starting and ending points will also be given to you. So your first job is to find the A matrix. And how do you do that? How do you find A? It's easy. A11 is, for instance, the response of the first sensor to the first input. How do you do that? You have this first sensor response and have this first light source. What you do is you multiply them function-wise, of course. Signal by signal or value by value, you multiply them. These 2 shapes you multiply and you integrate. So the multiplication will give you some new shape, and you have to find the area under that new shape. The function that I will be using in the take-home examination will be easy like these, where some analytical expressions can be obtained. One of them is a line, the other one is a circle. The line times circle will be having a function, and this declination part is another line and another circle. You multiply them and you come up with a function which can be integrated from a point, a starting point to an ending point. This is the first sensor response to the first input. How do you find the first sensor response to the second input? You multiply with the second input. For example, you multiply this sensor, the first sensor, this time with the second input. And as you see, some portion may overlap. As long as they overlap, you have to multiply them, get the function, and find the area under the multiplication region, multiplication function. So it will be the second sensor response, sorry, the first sensor response to the second input. What is the first sensor response to the third input? As far as I can see from this figure, it is 0, because they don't overlap. So their multiplication is 0, and when you integrate 0, you will get nothing. Then you continue with the second sensor response to the first input. They are overlapping, so they have a multiplication region. You find the area under that multiplication. The second sensor response to the second input. You multiply this rectangular box and this triangle. As long as they overlap, there is a multiplication, and then you find the area under the multiplication, and you do it with the third input, the second response to the third input. They seem to overlap as well. By the way, I can realize that what I did as an example for this illustration, for this exercise, is something slightly difficult, because the determination of this A would take some time. Probably for the take-home examination in the final, it may be easier shapes, more flat shapes, or maybe some even impulses. Okay, some of them maybe not a rectangle or a triangle, but an impulse. Then it would be, I guess, easier to solve the problem. So you're supposed to first find what is A, and then you will be given no, not this one. Oh yeah, this one. I'm sorry. You will be given a color. So this is the natural color, like this maybe. From this natural color, you need to find alpha i's. So what are alpha i's? The first sensor response to this natural color, the second sensor response to this natural color, and the third response to the natural color. What will they be? How will you find it? You will multiply these sensors with this large natural color to find one by one what are these alpha i's, what these alpha i's are. The first sensor response will give you alpha I. The second sensor response will give you alpha 1, sorry. The second sensor will give you alpha 2. The third sensor response to this color that I have drawn, the last one, natural color, will be alpha 3. So you will have alpha 1, alpha 2, alpha 3, and you will have A. If you have A and alpha, if these are given to you, then you're supposed to find what is beta. Beta is A inverse times alpha. And then I will ask you to discuss your observation. What could be the discussion? The discussion may arise if some of the betas happen to be negative. If that beta is negative, it means with these color sources or light sources at the top, it's impossible to reproduce this color, the natural color that I have drawn at the bottom, using these color sources, as long as your eye response is like this. Of course, it's not like that, but nevertheless, for the evaluation of the A matrix, something like that must be given to you. So these three shapes will be given to you in your examination, take-home examination. You will have a lot of time to evaluate the multiplication and finding the areas underneath. Okay, that's how. This is the kind of a question that you will encounter, and I'm giving you the hints about how to solve it. I'm showing you how to solve it. You just have to do it in the examination, during the examination. Okay. Now, if you interesting rules about the color matching, if these are known as the Grassmann's laws. The Grassmann's laws say that if a color C1 matches to another color C1 prime, and if C2 matches to C2 prime, then when you mix C1 and C2, it's like this, by the way, alpha times C1 plus beta times C2 matches to, this equality is not an equality of vectors or matrices or scalars. It's not mathematical equality. It means the colors are matching. Okay, we have a different issue going on here. This equality is not equality. It means color matching. Let me write it. Then the mixture colors also match, like alpha times C1 prime plus beta times C2 prime. So this is a color matching law. Let's see, law number one. And the other one is even in the subtraction domain, like if C1 plus C2 matches to C1 prime plus C2 prime, and C1 matches C1 prime, then you can just subtract from both sides of the equation, although it's not an equation. Then by subtractive methodology, C2 matches to C2 prime, it means. Okay, like regular addition, although I'm telling you that it's not a regular addition. And the third one is the transition. If C1 matches C2, and if C2 matches C3, then clearly C1 matches C3 by color transition. This is quite obvious, but nonetheless, we need to know these things in color matching. Because as you see, color matching is an indirect process of solving a set of equations. So even after solving all those equations, since everything is a linear process of linear set of equations, we can understand that that linearity helps us to have these Grassmann's laws, which act like regular normal summation or equation. There are some standard color sources. These color sources are essentially known as the color transformations. And transformations, let me say. They help us to determine or give names or give an illustration of the colors from the standard RGB. The standard RGB is not a standard RGB, but you can think of it like there exists a universal pure red, pure green, and pure blue light source, like in the form of a laser. And we have our human eyes, so RGB will generate the red values alpha, and the green values alpha, and the blue values alpha values. Starting from those RGBs, okay, and by multiplying it with a matrix, a 3 by 3 matrix, people have been trying to come up with a new, why did it become a little bit thicker than before? I don't know. The pencil is acting strangely. With the choice of this matrix that we have here, we come up with several color formats that are universally accepted. One of them, this one, for example, is YUV. The other one is CIE. The other one is LAB. And there is even XYZ, etc. Here, we usually try to separate the components of R, G, and B into 3 meaningful values. One of them being, for example, the luminance, which can be the Y coefficient or the L coefficient. So that would be the intensity, the brightness. It would be useful to have one of them to be the intensity, because of an ancient backward compatibility issue that we had from the transition of black and white or grayscale television to color television. And people just wanted to have a backward compatibility of televisions, saying that if you have still a black and white television, you may or may not buy a color TV immediately if the standard is enabled. You may have a black and white television, but the transmission or broadcasting is color. So am I gonna be able to watch it? And believe it or not, for the land transmission with the regular antennas, it is still backward compatible. So if you have a black and white television, you can still watch the intensity value of a color television, because it is split into 3 components, and those 3 components are neither R nor G nor B. It's intensity, one of them. And if you watch that intensity broadcast of that channel only, then you will be watching the black and white. The others are incremental color components, into which, if you add it, if you contribute as U and V by multiplying with the inverse of M matrix has an inverse, of course, you can always convert to RGB, and RGB values can be reproduced on the television with the necessary voltage values. But it requires M to be positive, valued in all 3 by 3 elements, because it will be done with a circuitry, and circuits tend not to have negative power. So M should be positive, and M inverse should also be positive, because that's your television. To convert YUV, CIE, LAB, etc. into RGB, again, it's an M inverse multiplication, and that inversion is expected to be performed using circuitry. If it is digital television, negatives are perfectly fine. But if it is electronics, analog, then these matrices, their inverses and themselves, should better be with positive values for an accurate reproduction. Otherwise, it would not be very accurate to for RGB to, let's say, YUV back to RGB. All the negative portions will make or will spoil some portion of this YUV, and all the negatives of M inverse will spoil further this YUV, and this RGB prime is therefore not precisely equal to the RGB. They will be different reproductions if you eliminate the negatives, or if the values are too large, again, that would be another problem. And in the television standardization, people started thinking about such meaningful matrices. And these matrices must produce the intensity to become a good contrast and reasonable intensity. So it must be something like a good average of R, G, and B must be in the first intensity output of the output vector, this one. This must be something like 1/3 times R plus 1/3 times G plus 1/3 times B. So we expect the first row of the M matrix to be 1/3, 1/3, 1/3. Or maybe green is more pronounced, so let's make it a little bit larger. Let's make the others a little bit smaller. But then the other components must also be reasonable in such a way that M is positive and M inverse is also remaining as positive as possible. As usual, I can't say it for today, but in the old days, there was a funny way of being too quick for doing something. It's an American way of doing things. It used to be, but of course things are changing now. And the Americans or the American companies were just jumping on the concept, and they wanted to be the first to broadcast color television. It was, I guess, Kodak or something like that, who were just jumping on doing things quickly. So they call it sometimes Kodak way of doing things. So they came up with a matrix, M matrix, and they say it's the standard, and we are broadcasting that way, and they called it National Television Standards Company, NTSC. NTSC has its own M matrix. The other TV standards came afterwards. So NTSC flooded the market. So people just bought NTSC television, so it became a standard in America at least, and in some other countries. But the Europeans just did not jump into that one. Then I think it was a French company, telecom company, who designed their own matrix, and they called it CCAN. I don't know what it stands for, honestly speaking. Why didn't I look at what it means from Wikipedia? I don't know. I should have done that. But I know what NTSC is. But there's also a funny anecdote, a funny joke about these things, because NTSC was a bad transformation matrix. It's not well engineered yet. So they thought it's an abbreviation of never the same color. Of course, it's National Television Standards Committee, but they called it never the same color. And CCAN, which was a French company, also did something, but it's not good either. And then came the PAL standard of the Europeans, which in Turkey we are also using that one. And in the majority of countries, this is still the analog television standard. And interestingly, they reflected these standards into digital format for some copyright issues. I mean, in digital television, we don't have an NTSC or CCAM or PAL or whatever. It's digital RGB with compression, and that's it. PAL, however, and NTSC are still struggling for copyright issues, so that the content from the United States should not be released directly into another country in Europe. So they are just putting some extra encryption, and they call it NTSC. But it's not this NTSC that we're talking about. It's just a copyright encryption. But in analog television, there was PAL, and again, I don't remember what this abbreviation corresponds to, but I remember the joke, and I believe that you will remember the joke in many cases. It is like at last. Oh, what's going on to my pencil? It's peace at last because it's a good conversion matrix with minimal negativity, and the intensity and the color differences are good. That's why the old day TVs of Europe were better looking better than the American TVs. The color in the American televisions or the old televisions are a little bit pale. So it's not only this is not only a standard for defining the number of rows or the synchronization frequency, which is 50 hertz versus 60 hertz or something like that. Of course, they are also different for NTSC and PAL. They are also different. The number of lines, etc., they are different. But the color transformation is the fundamental difference. And if you want to watch an NTSC tape video in a PAL video player in the old days, it was reproducing with false colors. It was a complete mess. So you may want to check out matrices of these on the internet, and you may want to check out the color gamut, chromaticity diagrams, and things like that. I'm sure you will be able to find a lot of interesting and very nice illustrations, and it will better help you understanding the concept of colors. And if you're interested, you may also want to pursue some research on this one for the reproduction. And as you see, the reproduction nowadays are mostly in terms of software, and sharpening, color enhancement, etc., are the things to go through for improving the color perception or improving the sharpness. Because the human eye is somehow something like it is open to illusions. You can have illusions and presume that it looks sharper and it looks with a better contrast, with better colors, etc. That does not necessarily mean that the color is well reproduced. For instance, the human eye system has this kind of a profile to this color profile, intensity profile I'm talking about. If you have this intensity profile like this, the intensity, this is the horizontal axis is space, and this is the intensity of a gray leveled image. So it's like stripes, okay, narrow stripes, starting from black up until white, and there are like, I don't know, 7 or 8 shades of gray. All right. So how do you see? How do the human eye see this? There is a spatiotemporal filter that is happening either in our brain or in our eyes to make this to be observed like this. First of all, the intensity profile is it becomes logarithmic. So the profile is curved a little bit like this from linearity. The linear intensity changes will not be perceived as linear intensity changes according to human perception. It will be converted to logarithmic, and the changes of intensity are happening like this. I'm trying to draw some ripples along the transition places. Those ripples mean that the whiter stripe edge, which is neighboring to the darker stripe, looks even brighter. Okay, so if you focus to here, that level is a bright level as opposed to the one below it, but that point, those points look even brighter. And conversely, these points, which are neighboring to the brighter stripe from the dark stripe, look even darker. So the abrupt intensity changes cause some incorrect contrast in our eyes. So our eyes actually observe it to be like this. This kind of nonlinearity plus filtering, it can be considered, these ripples can be considered as a sort of high-pass filter, but it's a spatial high-pass filter, space-wise, not a temporal or whatever. There is also a temporal filter, a kind of band-pass filter that is also valid, because if you look at some image for a long time, your receptors get accustomed to it, and they will burn out. And when you abruptly look at another place, you will see some false colors because the receptors will be saturated. That's also a temporal filter. All those spatio-temporal effects are inside our visual model. And for modern technologies, you not only have to make an accurate color reproduction, but you have to make an accurate visualization of a moving picture, for example, for playback of video, for considering these spatio-temporal effects. And everything from now on actually inherits from this human visual system, which is an excellent system, by the way. We claim it to be excellent because that's how we see it, and we want to see it that way, including, for example, the improved dynamic range. So there is HDR, high dynamic range. But high dynamic range, your dynamic range is limited with the dynamic range of your screen. But if you're improving in a software manner the spatio-temporal effects of an image, you start observing it to be containing a better dynamic range. That is called high dynamic range imaging or high dynamic range videos. It is all by software, and I would like you to study those things because they are still active research topics. Okay, so these are all the things that I would like to talk about regarding the color and color reproduction. The last things that I mentioned are not covered. I'm just mentioning about those. The thing that has been covered is the color reproduction, and you're responsible for that. And the question that can be asked for color reproduction is here, already given here. These shapes will be different, but the question will be very much similar. Okay? So that's all I want to talk about for today. Let me not start image enhancement and other issues. I'm leaving it for next week lecture, and we will proceed as much as time permits us. So I'm going to stop at this point. If you have any questions, you may ask now, or not, I will say goodbye. So any questions?
No, sir, thank you.
All right, very well. No questions then. See you next week then. Take care. Bye.